I'm Julio Soria from Monash University. My colleagues and I are very excited to have been awarded an Australasian Leadership Computing Grant to undertake a high-fidelity direct numerical simulation of a turbulent thermal boundary layer as an analog for a bushfire simulation. The overarching goal of our project is to simulate the complex interactions between fuel sources with different properties and the atmospheric turbulent boundary layer during bushfires, using high-fidelity direct numerical simulations that are usually referred to as DNS. As we have been experiencing over recent years, large bushfires with increasing frequency and severity are threatening local populations and natural resources and contribute naturally also to carbon emissions. Although bushfires have been an active area of research for decades, no verifiable theory of spreading is available to form the basis for high-fidelity predictions that are needed to manage fires more effectively and reduce their environmental, economic, ecological, and climate impacts. A recent study by Finney et al. Concluded that much of the complex multi-scale dynamics of bushfires, including its spreading, is governed by buoyant and inertial interactions rather than thermal radiation. That is, the dynamics of a turbulent thermal boundary layer, which I will call a TTBL. Turbulent boundary layers have been studied for more than a century due to their immense technological applications. Since turbulent boundary layers are responsible for the drag on all transport platforms ranging from aircraft to cars, as well as the transport of water, oil and gas through pipes and canals. However, the turbulent boundary layer is also important in a geophysical setting, such as the atmospheric turbulent boundary layer that surrounds the Earth and controls the weather, dispersion of pollutants, and naturally bushfires. Our project will employ high-fidelity DNS to a turbulent boundary layer with its kaleidoscope of complex multi-scale three-dimensional energy-containing structures, which you can see in the visualization that is my background, and will include distributed thermal energy sources to represent different fuel loadings. This will also allow us to investigate the effects of fuel loading parameters on the multi-scale spatiotemporal structure of the turbulent thermal boundary layer, as well as its mass, momentum, and energy transport properties. This is the first ever DNS at the scale and Reynolds number of a turbulent thermal boundary layer with distributed thermal energy sources, and can only be carried out using a high-performance computer like Gaudi at NCI in conjunction with a generous Australasian Leadership Computing Grant. The result of the planned DNS will advance our knowledge of the complex mechanics that are at play in bushfires, given that controlled experiments are extremely difficult to undertake and with accurate multidimensional measurements within bushfires virtually impossible. The advent and availability of high-performance computers like Gaudi is enabling detailed, physically accurate information about the process occurring in and around the bushfires to be obtained, and will allow us to develop improved fire spreading models, evaluate available large eddy simulation models, and develop new models based on the findings of this study. And furthermore, allow us to develop high-fidelity reduced order models with fast yet accurate predictive capability.